Good morning, all. On behalf of Vanimala Institute of Technology, Management, Principal, Directors, Head of the Department, Professors, Associate Professors, Assistant Professors of Department of EEE, welcomes you all for the second day of AICT sponsored short-term training program on electrical vehicle technology. Hope this day will be a better day for you. And I welcome Dr. Ilangovan for this session. Welcome you, sir.
Thank you, John, sir.
Today the session is going to be held on converters for electrical drives. So Dr. P. Ilangovan is a professor and HOD of Department of Electrical and Electronics Engineering as SRM TRP Engineering College, Trichy. So he did his undergraduation in Electrical and Electronics Engineering at Kambam Engineering College and a Masters of Engineering in Power Electronics Drive in Aruna Engineering College. And he completed his PhD in Anna University. He has a vast experience in teaching. He served as a teacher in several institutions, like he served as a lecturer in Dr. MGR Educational Research Institute, and he works as a lecturer in Kambam Engineering College. He served as assistant professor in SKP Engineering College, Thiruvannamalai, and he served as assistant professor in Department of EEE in Panimalur Institute of Technology, and he served as associate professor at Srinivasa Institute of Technology and Management, Chittoor. And currently he is working as associate professor and head of the department in SRM TRP Engineering College, Trichy. He had around 17 papers, published 17 papers in international journals, and he had participated around 21 international conferences. And he is a editor and reviewer of several journals. He is the editor of Book Publisher International, and he is editor of a Journal of Engineering Research and Reports, editorial board member of International Journal of Electronics Engineering Research, reviewer of IEEE Transactions on Power Electronics, reviewer of IET Power Electronics, reviewer of IEEE Transaction on Industrial Application, reviewer of Asian Journal of Mathematics and Computer Research, reviewer of Current Journal of Applied Science and Technology, reviewer of International Journal of Geography, Environment and Earth Science, reviewer of Applied Computational Electromagnetic Society. And he is a member of various professional societies like IEEE, IEAE, IEICE. So today he is going to present a session on the topic of converters for electrical drives. We feel pleasure to have you, sir. Welcome you for this session, sir, and I am handing over the session to you, sir. Please, sir.
Thank you very much, John, sir. Hope my voice is audible.
Your voice is audible, sir.
Okay, sir. Thank you. Thank you. So, first of all, I would like to thank the management of Panimalur Institute of Technology for giving this wonderful opportunity to share some ideas regarding converters for electrical drives during this 1 week STDP sponsored by AICTE. I would like to thank especially the department head, Dr. Rama Prabha ma'am and Dr. Deepa ma'am, for giving this very good platform to share my own views on DC-DC converters and drives arrangement. Thank you, madam. Straight away, I'll enter into the session and let me share my screen first. Hope my screen is visible to everyone.
Yes, sir, it's visible.
Okay. Today, the topic what have taken for this STTP is converters for electrical drives. And first, let me list out the content, what is going to be covered in the upcoming 2 hours. The first point, we do have some questions, basic questions with the participants, or it may be open to all, and related discussions. And the second part will be about the converters in general. And the third part will be the detailed discussion on family of DC-DC converters, because I have taken the DC-DC converters for today's session. Then the fourth part will be the research opportunities in DC-DC converters. Then fifth part, a little demonstration through simulation using MATLAB. And the last part will be a few tips on successful publication relevant to DC-DC converters. First part, as I said, we will start with a few questions. Usually the management people have this habit of asking 5 different questions along with one. So the first question is starts with why. Whatever may be the problem, they start with asking why. So my first question is, why are you looking for research opportunities? The first question will give you clear idea about the domains, right? So as a researcher, because this particular STTP focus on mainly the research scholars and those who are willing, eager to do research, right? So the researcher must think of it. Why we are looking for research opportunities? So the very simple answer for this question is we need to survive. We need to survive, first point, as a teaching faculty, because around 80 to 90% of the participants belongs to teaching profession for this STTP. So they want to survive themselves in their platform, then they need to look over research opportunities. Actually, this is not the actual answer for this question. We need to look after research opportunities to show some benefits to the society. That is why we are looking for research opportunity. Okay. Then the next question is, what is your problem statement? So once you have determined which domain you are actually going to work, then you need to identify what is your problem statement. Problem statement in the sense, these questions are not actually technical questions. First, you need to think why I am doing research and what is the actual problem from any particular domain, and in what way I am going to give solution for that problem. So this is the thing. Even if it is technical or non-technical, doesn't matter, but you need to ensure what is the actual problem statement, then only you can enter into the solution part. Then the third most important question is, where do you find space for research? So nowadays, most of the teaching community, they're struggling a lot. They're struggling a lot for the past 5 years. So as a teaching faculty, as a researcher, you all well known about it. We don't find sufficient space. We are just struggling to engage ourselves in research activity during the working 8 hours. So if you are the person who is looking for a space between that 8 hours, then your path will be very complicated one. The research journey is not so easy. The answer for this particular third question is, you need to look a space beyond that 8 hours. So most of the people try to engage themselves during that working 8 hours. If you are doing so only, if you are putting a boundary within that 8 hours, then the journey for research will not be so easy. So you need to go beyond that 8 hours and you need to have a space on it. And fourth one, when you are going to defend your research work successfully, so this is outcome oriented and end of your research, this question. So when, without planning the destiny, you can't able to travel. There is no meaning of a particular journey. So you need to define when you are going to actually defend your research work. Then only you can easily travel according to the path. So this point you should be very clear about it. And first thing, the fourth point is you need to identify the duration of your research work. When whom you are looking to support your work. So it's a trending one for researcher. We do find more than sufficient outsourcing people to support our research work. So if you are a person looking for such sort of outsourcing, then again I'm sorry to say this, your research work will not be a original work and you will be stuck into a big trouble after successful defense of your research work. So this is what I'm coming to say. The person who is right enough to support your work is your students. Students are the best asset in any part because we do have our own idea in research, but the student a step ahead. Their idea will be highly innovative. They need a little ignition from our side. So the person whom you are actually looking are our students. Either they may be a PG scholar or UG scholar. So we need to utilize the ideas and resource from students' side. This is the right way. What I actually executed and I actually formulated for my successful completion of my research work. The students are my big asset, big support. And finally, how we are going to defend it. So there are two different categories to defend. One is for the sake of degree. Second one for the sake of wisdom. So it depends on individual actually whom they are going to choose. So if you are looking for wisdom, it may take six years average. If you are looking for a degree just alone, for a PhD degree, it may take only 3 to 4 years to complete. So the choice is yours and the ball is in your court. So before entering into a particular topic or a particular work related to research, you need to ask all these 6 questions and you are supposed to give answers perfectly for all these 6 questions. Then only your journey will be very smooth. Then the second part. Now we are entering into the actual topic of today's session. So as I said, the topic is converters. The converter is a simple generic term. Okay, it does not give any meaning at all. So before saying about converters, we need to ensure what is actually the power electronic system. It's a fundamental thing. So I have shown you a simple block diagram which shows power electronic system. So it has a power input, power processor, power output, load, and there is a feedback path with a controller with a reference, right? So this diagram will show you the clear power electronic system and where actually the converter comes into role. So here we don't know what sort of power. The input power is either AC or DC. We don't know what is the actual power output. It depends on completely the load part. So if the load which requires DC, then power output must be DC. If the load requires AC, then the power output must be AC. So based on the requirement of load and based on the available resource, the power processor part plays a vital role, and this is where our converter system lies. And the complete control of converter system is dealt by this controller. The controller, n number of controllers are there available in our market today. And we are going to end up the session, we are going to see very few. And I assure you that you will be taking a bag and bags of idea for DC-DC converters. And hope end of the session, people may simulate a simple DC-DC converter based drive. So as I said, converters are a simple generic term, right? And it is further classified as AC to DC converter, which is called as rectifier. Then DC to DC converter, we call it as choppers. DC to AC converters, we call it as inverters. And finally, AC to AC converters, it is a cycloconverter. So right here I have shown another diagram which shows the converter job. If it is AC to DC conversion, then it acts as a rectifier, and rectifier further classified as controlled and uncontrolled. If it is controlled, then there may be a semiconductor switches. Okay, it may be either voltage controlled or current controlled switch, which we are using for that converter circuit. And if it is uncontrolled, there is no need of using any controlled switches. Simply we can go with a diode. A diode is the best example for uncontrolled power semiconductor device. And when we require actually the DC to AC, so DC power to AC, then the converter which is used as a inverter, it operates in inverter mode. The power reversal may take place. So this is the job, and in between there lies one conversion. So we have to speak about that DC to DC. Nowadays, why I have taken this particular topic for today's discussion is, we do have enormous research problems and enormous solutions for AC to DC converter as well as DC to AC inverter. You can, if you search in any platform like IEEE or any elsewhere journals, you can get thousands and thousands of papers in inverter as well as converter. Because searching, as I said, I started with the first question: what is your actual problem statement? Okay, so if you are a researcher looking for a better research, then you start look on DC-DC converters. Why I'm saying, I'll let you know and I'll let you justify the actual point in the upcoming slide, right? So next thing, the history of the different converters. We are very familiar about the history of rectifiers. In 1960s, before that 1960s, AC to DC rectifiers were constructed using mercury oxide rectifiers. So you can see the image right side of the slide. This is the mercury oxide valve. It's a rectifier used before 1960s, and in some industries, that is automobile industries, still they are using this sort of rectifiers for their work. And now it's a trending to replace these sort of mercury oxide rectifier with SCRs. Okay, so you can see how complicated design, and it is not at all compact. Before 1960s, for converting a AC power to DC, they have used a huge system, huge mercury oxide rectifier. And during 1960s only, the role of SCRs play a vital role. So in 1960s only, it started evaluating itself, and it was successfully developed during 1960. And a simple circuit, how AC to DC conversion is done is shown here using a diode, right? So we are very familiar. The input is AC signal as the source is given, and when the diode is used, this is, let us take it as a VI, and the load voltage is V0. The voltage across the load is V0, and in between source and load we have used a diode, and the job of the diode is to rectify. How it rectifies? Whenever the anode is positive with respect to cathode, this device is forward biased and the supply is directly connected to the load. And we do know, if there is no any other element used, no more parasitic elements in between the source and load, so directly it takes the cut section of the positive off cycle of this supply. So you can see this up to this. The first off cycle, the cut section of supply will be the load voltage. And due to the power reversal, in the second off cycle, the supply is reversed. The polarity gets changed and the anode is made negative with respect to cathode, and this goes reverse biased and complete supply is isolated and the load is open circuited, and there won't be any voltage during this duration. Again in the next cycle, again it starts a cut section of positive cycle. This is how. And we can have a question in our mind, sir, we are talking about AC to DC. Is it a DC signal? No, exactly not. So this is not a DC. This is completely polluted DC signal with high harmonic distortion, right? So this will be average, or this will be taken into load by means of a filter arrangement in the load terminal. Again, it gives load complication. Circuit design is complicated, right? So a simple AC to DC rectification operation I've shown you. Then the second part, the top part. So this slide will give you clear idea why you need to take DC-DC converters for your research. You can see at present we do have 500 existing topologies. Okay. So if you take AC to DC or DC to AC, as I said in IEEE Explorer, if you sit and search, you can get thousands and thousands of papers related to AC to DC and DC to AC. And even you can get papers in DC to DC, but not beyond the second generation or third generation of DC-DC converters. So out of this 500 existing topology, you can see very few. Okay, 10% of this 500 existing topology are discussed in the existing papers. The remaining 90% of topologies, the researchers have never touched. And you have a better scope when you start doing research in DC-DC converters, and it may fetch you in the successful publication, and easily you can defend your research. And this point I'm speaking about those who are doing for degrees, those who want to complete their research very soon, right? So, but you can do your own contribution, own innovation in those sort of converters. The converters are there, but we need to do something for some application. We have to choose it. So that is why I mentioned that DC-DC converters will find a very good scope and publication point of view. And we do have the applications like DC motor drives, communication equipment, mobile phones, digital cameras. So in all these applications, we do have DC-DC converters in different configurations. And the major problem while using DC-DC converters, the first point is mathematical modeling is not so simple. So because a DC-DC converter alone, if you are using, just it will perform its job. But when it is cascaded to any sort of applications, any sort of drive, then the mathematical modeling of that particular DC-DC converter is not so easy. It's a vital task. So that is a major problem. Then traditional method they are following, which one is the impedance voltage division method. So we all know voltage division rule. So with respect to that rule, they are designing the DC-DC converters for any sort of applications when it is cascaded with the drive. Then we need to check the power rate of DC-DC converters. So here, the DC-DC converters are not a simple circuit. It includes parasitic elements, two major parasitic elements, that is inductor and capacitor. These two reactive elements plays in voltage boosting and voltage step down. So only the role, instead of battery, the capacitor doing the job. So it injects the reactive power, and the reactor absorbs the reactive power in some means. So you can see, if you want to design, as I said, first problem is the mathematical modeling. If you are if you are designing a circuit with transfer function approach, then the order of the transfer function is almost equal to the number of energy storage elements. Energy storage elements in the sense, the inductor and capacitor. Okay, if you take a simple DC-DC converters with 4 inductors and 4 capacitors, a simple converter, any type. So 4 inductor and 4 capacitors, then the mathematical modeling, that is the transfer function of that circuit is in the order of 8. So just think of, if 8th order system is going to be analyzed, how complicated, whether there is any stability issue, if you are giving any input to that particular system, how can you analyze its stability, how can you analyze the response of that system? That may give high complication, and the gain tuning is not at all so easy, it is a complicated one. So this may again fetch few problems. Then the next point, how can a large power can be used in energy system DC-DC converters? The next question. So as we are discussing about the transfer function approach, the number of parasitic elements combinedly equal to the order of the system. So if we are talking about in terms of power, if I'm reducing the number of parasitic elements, obviously it may be applicable for low power applications only, right? So when the number of storage elements gets increased, then only it deal the high power. So I want to make use of more parasitic elements, and I want to make the mathematical modeling as simple as possible. So you need to look after how can you reduce. So that gives a clear idea on switching techniques. Even if the number of elements is used more, you can reduce the number of elements by having the advanced DC-DC converter options. That is why I told you 500 existing topologies are there. If you go generation by generation, they have simplified the circuits by reducing the parasitic elements, by maintaining the order of the transfer function. There are two different approaches are there. When you are dealing with the circuit design mathematically, one approach is transfer function approach. It is applicable only for linear system with zero initial condition. And that is, I can say it is not much accurate. It is approximated one approach. And the second one is very accurate, that is state space approach. It considers zero initial conditions. It does not consider zero initial condition. It considers the original initial condition of any parasitic elements, right? Then the power rating, the major part, whenever you are choosing the DC-DC converter, the power rating plays a vital role. It's an important factor to be considered, and which drive you are going to apply. So here I have given a few relations, that the energy transfer rate and maximum power transfer. So energy transfer rate del E is equal to L by 2 I square max minus I square minimum. So this I square maximum and I square minimum is nothing but the output current transfer that is transmitted from input end to output end of a DC-DC converter. So it varies, the ranges, the energy level transfer, energy transfer rate varies between that maximum current limit to minimum current. And the major point, the constant one is the inductor, the value of inductor. Choosing the value of inductor plays a major role. And maximum power transfer. So you can easily design a converter with respect to this expression. You can identify how much power can be transferred by using a DC-DC converter with this simple multiplication. The frequency of the switch that is used into the change in energy. This expression into the frequency. This F is nothing but the frequency of the switch which you are going to use in DC-DC converter circuit. Then the next circuit, DC to AC, inverters. As usual, before 1960s, it is not at all widely used. Very few applications relied on the inverter. And after in 1970s, a fractional horsepower, that is 0.5 HP motor drives, started using this inverter for process automation. In 1980s only, this inverter found a wide usage. Most of the industrial applications highly rely on this inverter, because we are now standing in the industry 4.0. If you start looking, go back industry 3.0 and 2.0, the process automation. Today we are using IoT technologies for controlling any sort of drives. Today in industries, they are just implementing all these technologies for controlling a process. In the last generation, they have automized by means of PLCs or by means of any closed loop elements, right? So during that period and all, the inverter, for example, if you take a motor, I want to use that motor for conveyor, and my conveyor does not require any manpower. This is 3.2, I'm talking industry 3.2. So that converter will be designed with respect to a closed loop control, and accordingly the frequency of the motor is varied based on the load. So I want to shift to a package of some 20 kg from one stage to another stage. My motor has to rotate some 300 RPM for a delay, for a time duration of 50 seconds. So this is the thing. So my frequency of the inverter, output frequency is decided accordingly. So 50 seconds, the inverter will produce the same frequency. And at the end of 50th second, the inverter turned off. Again, after loading the second job, again my motor starts. The same frequency is delivered by the inverter, and the motor rotates in 300 RPM, and then it distributes the second. So here you can observe there is no manpower. Okay, that is the ultimate aim of Industry 3.0. If you go back Industry 2.0, there is a man standing on it, and they'll be using a motor which is manually operated. Okay, there is a man, right? So they'll be turning on the switch of motor, and they'll be loading that weight on the conveyor belt, and they will turn off when it reaches the destiny. So this is what the Industry 2.0. And when it comes to Industry 1.0, you don't find any conveyor arrangement. To shift a job from one stage to another stage, complete manpower is utilized, right? Actually, hardly speaking, the Industry 4.0 or 5.0 reduces the manpower, and it may increases the employment problem issues. We are technologically developing, technologically fetching towards a height, but it indicates the employment opportunities are highly reduced because of this. Here in industry, we are right now moving towards Industry 5.0, and I make sure that only people, those who are skilled enough to compete with the automation process, will survive in industries, either engineers or any sort of technical people. And then next, conversion techniques. What sort of conversion techniques we do have? We do have two different general conversion techniques. One is pulse width modulation, and another one is multi-level modulation. And pulse width modulation, you can see it is suitable for inverters, and it is less convenient. Why it is less convenient? We need to have more number of signals to be processed to have a complicated gate control circuit. And the multi-level inverter that was invented during the year 1970, and it has a further subclassification like diode clamped circuit, capacitor clamped circuits. Then the last type of converter is the AC to AC converter, and before 1960 it is not widely used, but when it comes into role, it was used for low power applications like heating system for temperature control, and light dimmers in theaters, even in nightclubs, even in rooms, newly constructed buildings. If you want to go for a light dimmer, they can use AC to AC cycloconverter arrangement. They'll be opting. For these sort of application was used. The major drawback is whenever power electronic circuit is used, two major problems will come along with it. One is poor PHD, and another one is poor power factor. Then we are going to see the converter's role in applications directly and indirectly. So in the direct way, I have shown you three different diagrams. So what the converter job in this direct applications, direct. So first diagram shows you, as I said, it's a conveyor, right? So you can have a converter, a man has operated the control circuitry manually, right? So this is not the actual converter job. Here we do have a converter, and that was operated to control the rotation of the motor, and that is not manually operated, direct, right? So if this is a DC motor, if the motor used is a DC motor, I can use a DC-DC converter directly, and I can put a battery here. I can put a battery. So from the battery, the converter receives supply, and based on the gating sequence, the DC motor speed is controlled, right? So this is the direct application of the converter in application part. There is no other stages are involved. In second diagram, you can see there are two stages. So one is the generator side converter, and another one is grid side converter. So in both ends, here the power that is generated from the wind turbine that was converted, and it is stabilized in this part. So in the linked part, it is AC link, it is not DC link, it is AC to AC conversion. and we do have a link which is obviously it is used in some cases. They may use a AC to DC converter in the front end. Again, they will put a chopper DC to DC converter in the middle end. Again, they will use an inverter in the grid side, right? So by integrating the power, AC power that is generated from the wind turbine, and they will make use of the grid power parallelly. They will synchronize it. So this is the direct converter part in the application. Directly the grid is connected. And the third one where the direct role of the converter plays is the energy storage elements. So we do have solar energy conversion systems, right? So in solar energy conversion system, the power that is generated is DC from PV array. So that DC is will have more number of ripple content, oscillated one. So I want to make ripple-free DC, and the same DC is to be connected to battery banks. Means I want to go with the converter which stabilizes the oscillated DC, right? So PV array, converter, and batteries. So here they have given inverter arrangement and all. It is not required. You can see this part alone. It is another direct role of converter in application. Now coming to the indirect role. So the converter, most of the applications, why we are going for drive. Now coming into the back end of the topic, drive arrangement. Why applications are drive based? Because it is process automation. We are standing in the industry 4.0 with process automation. 80% of residential as well as industrial applications are based on motors. So that is why a control is needed for motor, and combinedly we call it as a drive. So two different motor types are there. One is DC and another one is AC. So if the motor opted for a drive arrangement as DC, then we call it as a DC drive. If a motor opted for a drive arrangement as AC, then we call it as AC drive. So for this topic, I have taken a simple induction motor drive, and why it is actually preferred. I want to say why I have taken this induction motor drive for today's topic is it has upgraded process automation. Comparatively with the other motors, it has upgraded process automation, and losses are highly minimized, and it is soft started. Then thermal and mechanical stress on motor is very low comparatively with the other motors. And the third point is the various power quality issues. Whenever we are working on a drive, these parameters are very perfectly. Particularly, we need to note down these parameters without compromising the quality of these parameters. We need to design a drive. First point is the total harmonic distortion. Most of the people, if we ask what is total harmonic distortion, they may explain it in terms of formula with respect to fundamental frequency and second order, third order, like that. Simple explanation for the total harmonic distortion. Let me give you. Here we do have a simple sine waveform. Hope I'm just drawing this. Let us take this is having 50 Hertz frequency. This sine wave has 50 Hertz frequency. And I want to speak about harmonic. So in subjects, most of the textbooks, they may say the triple N harmonics are very critical. The triple N harmonics are the problematic one. And the even order harmonics will not be there. Why? How it is existing? Why the even order harmonics are not at all existing? So here I'm talking about in terms of frequency. What will be the time period of this one complete cycle? What will be the time period of my waveform? I need to show that it is 0.02 seconds. So inverse of frequency, it is 0.02 seconds. The total time period it will take for one cycle is 0.02 seconds, and this is one cycle, right? And this is F1. This is a fundamental first order. First order is 50 Hertz. It is 0.02 seconds. So the second order is, it is even order. So even order, what will be the frequency? It should be 100 Hertz. So the second order has into 2, 100 Hertz. So for 100 Hertz, what will be the time period, total time period for one cycle is, we need to divide 1 divided by 100, so obviously it is 0.01. So it has 0.01 time period and the waveform will be sketched like this. So this is order 2. So it is second order. And now, as I said, the even order will not be a problem and it will not exist. Why? Because you can see the even order, it spins like this. It's also a sinusoidal. And the end of the even order, what is the fundamental amplitude? Right? So this is the fundamental frequency component. And the amplitude at the end of the second order is obviously 0. So the amplitude is 0. So that is why even order harmonics are not at all existing. Even if you derive it for fourth order in the sense for 200 Hertz, that will be very minimum. That will be very, very minimum, low. That's why it is not at all a problem. So when you are analyzing with respect to spectrum, it will show you very clearly. And the third one is 150 Hertz. For 150 Hertz, if you take 1 divided by 150, it will be giving you 0.006. So somewhere here it will come. So this will be the third one. If you take the end of the third harmonic, just see the fundamental, just compare the fundamental one. The amplitude during the termination of the third order will be maximum. So this maximum amplitude. So that is very complicated. Similarly, if you take 3, then 9, like that, 9th order, like that, if all the triplet harmonics has the maximum amplitude of fundamental component, so that is problematic. So what it results actually, this total harmonic distortion will result in heavy losses. And further, indirectly, it may affect the power factor of the supply end also. Then voltage and current oscillations, in the sense it's a ripple. So these 3 parameters are most importantly noted when we are designing any drive. Without compromising these 3 factors, the drive has to be designed. Then the next point, what is the role of the DC-DC converters in the drive? Very major, very simple. One is I want to boost up the level of voltage. So that is why I'm going for a DC-DC converter. First point. Then I want to stabilize or regulate the DC link voltage. So why should I boost up the level? What is the need for it? Because in a drive, it has 3 stages sometimes. It has 2 stages sometimes. So if it is 3 stages, first stage will be the rectification stage. Second stage will be the DC-DC conversion stage. And the third stage will be DC to AC inversion stage. So if I take this particular example, so first stage is AC to DC. Then see. And second stage is DC to DC. And my third stage is DC to AC. Here, the rectified DC, even if it is controlled, it will not be the exact DC. It may have ripple like this. You can see the ripple content. So if the same ripple is given to the inverter part, then there may be a chance of malfunction in the inverter circuit. And if you are giving the same to any battery also, the charging rate of the battery and discharging rate will be very rapid. So that may shorten the lifetime of the load, or it may shorten the lifetime of the inverter. So I need a separate arrangement which is DC-DC converter, and it performs the job very clearly, and this ripple content is highly eliminated by means of capacitors present in this DC-DC converter part. So the ripple-free DC is was obviously attained at the end of DC-DC converters. Then, as I said, why I need to step up, why I need to boost. Somewhere here I'm not going to talk about the buck converter, only boost converter or pumping up of DC voltage is most required for drive arrangement. That is why I'm going to talk about only the boosting level of converters. So based on this two factor, we are going to see few DC-DC converters in the upcoming slides. Now entering into the heart of the topic. What are the family members of DC-DC converters? You can see, as I said, there are 5 different existing topologies or configurations are there in DC-DC converters. That 500 topologies comes under the 6th generation. The first generation is classical or traditional, what we are again and again using for our research work, what we are again and again dealing with the simulation or whatever. So the second generation, it is a multi-quadrant converter. So these converters will perform like a 2-quadrant operation or sometimes 4-quadrant operation, and the power rating will be very medium. So you can say hundreds of watts or higher, because that is the job of the second generation DC-DC converter. And the third generation DC-DC converter, we call it as a switched component converters. And switched component converters, how it is made? The next question arises. Either it is made up of inductors and or capacitors. Sometimes switched inductor and switched capacitor circuits are there. So that type of circuits comes under this third generation DC-DC converters. Then coming to the 4th generation. So in 4th generation, in general, we call it as a soft switching converters. And further, it has 4 different types. In soft switching, very clear in most of the textbooks, they have given resonant switch converters only. The remaining load resonant converters are there, resonant DC link converters are there, high frequency link integral off cycle converters are also there in 4th generation DC-DC converters. Then coming to the 5th generation converters, simply it is called as synchronous rectifiers, synchronous SR DC-DC converters. And it is developed based on the computing technology. So the synchronous rectifiers are obviously developed based on the computing technology, and you don't find sufficient papers on it. In 6th generation, the last generation, I cannot say it's a last generation, still the generation goes on. Now we are standing in the 6th generation, and multi-element resonant power converters are there. So it has multiple energy storage elements, and it is MER converters. We call it as MER, multiple energy storage element resonant converters. So in this, we do have current resonant inverters also there. Mostly these type of converters are utilized in UPS. UPS sometimes high frequency annealing apparatus also uses the 6th generation converters, but very few papers are there in this. You can see for today's topic, we have taken only 1st generation. In the 1st generation, let us see. First, we'll see if you take any one converter among this 1st generation itself, your research will be very easy, and you can defend it within 3 years. You can put a number of papers in this converters itself. So it's a 1st generation, and we all familiar with this buck converter. The job of the buck converter is to step down the voltage. Boost converter is to step up the voltage. Buck boost converter is to step down as well as step up the voltage. So these are called as fundamental converters, what we are actually looking, what we are actually working. In addition to that, Buck converter is there, SEPIC converter is there. Then 2 more converters accompanied with this fundamental converter. One is voltage lift converter and another one is super lift converter. I want to mention this name. It is Leo converter series. Leo converter series. I want to give credit to that particular inventor of this particular DC-DC converter. So there is a separate textbook is there that is written by Fang and Leo. that is advanced DC-DC converters. If you see to the textbook, all this, what I said, all the 500 topologies, out of that, around 30 to 40% of converters was discussed by Fang and Liu. All comes under Leo series. So you can take any one sort of converters and you can analyze its stability. You can make use of that particular converter for your drive arrangement. You can analyze the continuous current mode of operation, discontinuous current mode of operation. Any one topic, if you look after, immediately it leads to one publication. I assure you that. So what is the difference, sir? Voltage lift converters, super lift converters are there. Again, it is classified as 7 self-lift converters. So that 7 self-lift converters are self-lift converter, self-lift positive output, Leo converter, reverse self-lift positive output Leo converter, self-lift negative output Leo converter, reverse self-lift Leo converter, self-lift step-peak converter, enhanced self-lift positive output Leo converter. I am not listed in this because due to space availability, I can't able to put it here. So these are the 7 self-lift converters. Along with that, positive output Leo converter, negative output Leo converter, modified positive output Leo converter, double output Leo converter is there. And the another classification, super Leo converters. It has positive output cascaded boost converter, negative output cascaded boost converter, positive output super Leo converter, negative output super Leo converter. So here they are talking about what is this positive output and negative output. Very simple. Polarity reversal in the output terminals. If the polarity is plus minus as per the load requirement, if the polarity is minus plus, then we call it as a negative output. That is the only difference. And the polarity reversal changes. If the same configuration with a slight modification, they have designed a new converter. Only one converter they have initially taken, and slight modification in the output end to reverse the polarity, and they have named as negative output. So the cascaded boost converter, in the sense, it has different stages. They have taken 2 boost converter and cascaded the 2 boost. That's it. They call it as cascaded boost converter. If the output is positive output, then they calling it as positive output cascade. Similarly, and the most important, I'll let you know what is the actual difference in this matter. So the 2 converters, voltage lift technique and super lift converters, we have seen. What is the difference, sir? So 2 differences. The voltage lift converter deals with arithmetic progression. When it comes to the super lift converter, it deals with geometric progression. You need to know what is arithmetic progression and what is geometric progression. You can take this number series sequence 1, 2, 3, 4. There exists a common difference 1 between first number and second number 1, between second and third 1, third and fourth 1. There is nothing. If you take this sequence 3, 5, 7, 9, 11, there exists a common difference 2. So this type of progression in the sense, if I am giving a particular voltage for each and every cycle, the progress of the output voltage is based on this sequence, then I say it is arithmetic progression. And the voltage lift converter uses this algorithm, this sequential progressive technique. That is why it has some limitation. But the same progression in boost converter and all, you can, while explaining the circuit, I will tell you how this progression takes place. In super lift, you can take the first one, 2, and the second one, 6. So there exists 4. The difference between the first digit and second digit is 4. If you take 6 and 18, there exists 12 difference. Similarly to ego. But there exists a common term 3, that was the multiples of the first element. If you multiply 2 with this 3, that will give 6. If you multiply 3, the same element, with 6, it will give you 18. If you multiply 3 with this 18, it will give you 54. These type of sequences with respect to a constant term, we call it as geometric progression. If you look after, for initially 2, the next cycle, the voltage boost up is 6. But when it comes to here, 3 means 5. The common constant is 2. Okay. So this 2 and 3 indicates the voltage transfer gain. I'll let you know when I'm explaining the diagrams circuits. So the DC link converters in induction motor drives. We do have seen the fundamental converters, buck converter, boost converter, buck boost converter. The basic problems in all these fundamental converters are the voltage lift up is limited to only 2 times, and the output voltage will be high ripple. There is huge amount of oscillations are there, and it requires a bulk capacitor, right? That is why we are not going to concentrate on these 3 type of converters in practice right now. Then we need to talk about the active power factor correction circuits. So it is not only the job of the DC-DC converter to voltage boost up and stabilize the DC link voltage. In some places, as I told you, the drive has 3 stages somewhere, and when the AC supply is utilized as a source for a drive, you need to ensure the power factor should be unity, near unity, not unity, nearby unity. So the DC-DC converters, which is opted for the second stage, should take care of the power factor correction. So conventionally, the uncontrolled rectifier with the boost DC-DC converter done the job in the front end. Phase controlled rectifier without any DC-DC converter done the job. Then phase controlled rectifier with the boost converter done the job. Right? So the number of stages further increases, the number of complicated elements increases. So on the whole, these are the problems sorted out when you are using the fundamental DC-DC converters. The mass of the inverter, space requirement, the losses, cost, DC link voltage regulation, everything affects the circuit, the design of the drive. That is why the buck boost or cut converter, SEPIC converter are mostly not preferred to the drive element. We are talking about why. Mathematical validation. Sir, you are saying that this is not preferred. A simple parameter I have taken. You can see the boost converter. We know the working principle very well. I just want to skip the fundamentals, which is obviously familiar with the participants. When you turn on the switch, the current circulates, and this is short circuited. It's energized the inductor, and that time the diode is reverse biased, the capacitor supplies the load. When the switch is turned off, the stored energy will release the energy, will discharges, and the current that is circulated and the diode is forward biased, and combinedly the current from the capacitor and this element supplies the load. So initially in the first chain, capacitor supplies the load and it discharges to 0. Sorry, this is not the error bar. And a part of current charges the capacitor, and the remaining part supplies the load. This is how the draw operation happens in boost converter, and its output voltage is given by 1/1 minus conduction duty into VIDC. Just take this gamma is equal to 0.5. If you take gamma is equal to 0.5, I'm fixing this conduction duty, that is T on by T, to be 0.5. So if I fix it, then what will be the obvious solution? 2 into VA. If I give 5 volts as my input DC, then at output I'll get only 10 volt. The voltage transfer gain is 2. This is water progression. This is water progression, which I told you previously. Then among that voltage lift converter, we have chosen elementary positive output relay converter. So this is also another type of advanced DC converter, and it has the output voltage expression, that is gamma by 1 minus gamma into VADC. Same, let us take gamma is equal to 0.5. So what will be my voltage transfer gain? So it is 0.5 divided by 1 minus 0.5. Obviously, whatever voltage I have given, the same voltage will be there, right? So if I give 5 volts as input, output voltage will also be 5. So that is how, yes, any questions? Any questions? Any questions? Okay. So for the same voltage, the circuit does not require to be, does not boost up, it does not buck the voltage. But the advantage of using this elementary positive output Leo converter is the ripple. The ripple is less than some 5%. The oscillation of the output voltage will be highly reduced. That is why we are going for a little complicated circuit arrangement, and this comes under advanced DC-DC converter. Then another circuit we have taken, enhanced self-lift. I told you I have sorted 7 different self-lift converter. Among that, enhanced self-lift converter we have taken, and that has the output voltage 2 minus gamma divided by 1 minus gamma into VADC. For the same 0.5, if you substitute same 0.5, we'll be getting 1.5 divided by 0.5. So 3 times the voltage transfer gain will be 3 times. So if I give 5 volt as input, then my output voltage will be 15. So 3 times it's boost up. And also the ripple is less than 5% in this circuit. But if you see the number of parasitic elements, here one inductor we have used, another inductor, there is a capacitor, another capacitor, one more capacitor, and 2 diodes. So these number of parasitic elements we have used. Then coming to the superlift converter, you can see both the expressions. Here also it is 2 minus gamma divided by 1 minus gamma into VADC. Here also 2 minus gamma into VADC divided by 1 minus gamma. So whatever may be the conduction duty, the voltage that is converted, that is stepped up is 3 times that of the input voltage. But when it comes to the number of parasitic elements, you can see only 2 capacitors, 1 inductor has been used comparatively. So I have shown you some 4 different converter circuit, and mathematically for different conduction, for different values of gamma, you can see the voltage transfer gain. And if you take the boost converter, the values are very minimum, and only the average, the most of usual, in practice, the conduction duty for open loop system is 0.5. So for 0.5, if you look at all the DC-DC converters, you can see the difference. Boost converter will perform only twice that of the input voltage, so it is not suitable. And the elementary positive output Leo converter will perform the same voltage, will give the same voltage as that of the input, but the point is, the advantage is the ripple is highly reduced. Because of the ripple conductor, we cannot choose this particular converter. And when it comes to enhanced self-lift positive output Leo converter, it gives 3 times that of the input voltage. It is okay. But the thing is, the number of parasitic elements, the compactness of the circuit is very complicated, and it is not at all suitable. Now the only choice is the superlift converter. So I can put 2 tick. This is how you have to mathematically compare and mathematically validate the choice of the superlift converter for my drive arrangement. Next one, the 4th part, the research opportunities in DC-DC converters. So here in this part, I'm going to show you Yes, someone is speaking, I think. If you have any questions, you can ask. Right. So now we are entering the selected DC-DC converter, how it is going to be designed, how it is going to be simulated for a drive. First, I have taken it for an open loop drive, induction motor drive, and this part will never explain you the drive end, how the closed loop control circuit are designed for the induction motor. Only we are going to focus on the DC-DC converter part. So a simple simulating model, you can see the diagram of the simulating model of a DC-DC converter based drive. So only this part we are going to look after. Only this part, DC-DC converter. So I have taken a DC-DC converter. As I shown you 5 different converters, and we are going to justify it through simulation. So it is the source, DC source, and the source is connected to this converter part, and the converter output is directly given to the inverter, and the inverter output is directly given to the induction motor. So low rated 0.5 HP induction motor we have chosen, right? So the only factor we want to check is the output voltage of the DC-DC converter. How about the output voltage? Now first, the model of a boost converter. You can see the boost converter circuit, the same circuit I have given in the subsystem. Only thing, it is working in open loop. So I given a fixed pulse, that is 0.5 duty cycle I have given. And this is the part where you need to modify the parameter. This is a circuit for boost converter, and this is a circuit for voltage lift converter, the same circuit what we have seen previously in terms of simulation. And nothing, the values of capacitor, inductor, everything are listed in the table. And the circuit for super lift Leo converter. And first result. So these are the values. Here, according to the mathematical justification, we can take one converter from fundamental, that is boost converter, because in induction motor drive, most probably we have seen boost converter usage. And another converter from advanced DC-DC, that is super lift Leo converter, and the values almost same values, nothing special, no change at all. The values of inductor, capacitor, everything is same as that of boost converter, whatever we are using in super lift converter also. And the device which is used is IGBT. The first result. If you look up the DC link voltage, as I said, only one parameter we need to ensure for this topic, the DC link voltage. In boost converter, you can take for 150 volt. For 150 volt, the output voltage is 300, twice that of the input voltage. Into 2, 150 into 2, they have got 300 volt. And this is not the actual output. In the actual output, I'll show you the MATLAB simulation. Then you can see how ripple element will be around 200%. I have used one mean block to eliminate the ripple in my simulation. That is why here the ripple is not shown. And I'll show you in the simulation part. And you can see the initial overshoot of that voltage, it goes beyond 500 volts. So when it is directly used to any battery, if this boost converter is directly connected to a battery, if my voltage at the start time goes beyond 500 volts, then the charging rate will be maximum, and then it takes 0.2 seconds to saturate. Then only the stabilized output is received from the converter, and this may affect the lifetime of the battery. If it is used, just think of the converter is used in the front end of inverter, then imagine for 500 plus voltage DC, if your inverter is designed for only 300 to withstand, then what about the result? It may malfunction most of the time. So, but when it comes to the super lift converter fed induction motor drive, there is no overshoot, and you can see it is 450, which is 3 times that of my input voltage 150. 450 volts, it gets settled, and see the rise time. It is less than 0.1 second. Rise time is very low, but here it is settling time is 0.2 seconds. The steady state period starts with 0.05, not less than 0.05. And then talking about the DC link current, here also the current goes beyond 8 amps. It may affect the fusing. If we are using some fuses to protect the overcurrent, then frequently your fuses gets damaged. But when it comes to super lift Leo converter, the current does not go beyond 3. Here, the point I would like to say, this does not get settled because it's an open loop system. The current will get saturated after 0.8 only. And then talking about the line voltage at induction motor terminals, obviously there is no much different because the inverter is separately controlled by the gate sequence. Here, by using the filter, it gives a clearer picture like sine waveform. and the current waveform. This is also does not have any impact on DC-DC converter. So the point what I am coming to mark here is, whenever you are discussing the DC-DC converter role in drive, it will never have impact on inverter performance, because inverter is separately controlled with respect to the motor parameter. If it is feed forward controlled, then it will have the impact on inverter output. For our system, what I have designed, what I have shown you, it is not feed forward control, it is an open loop, right? So there is no impact on DC-DC converter on motor performance or inverter output. The most important. So even though the inverter is standalone, it is operating, just look at the speed response. So for both the cases, the induction motor terminal voltage, the line voltage is almost same, but the speed response, here it is not at all settled for 1 second. The speed response, when my drive arrangement uses a boost converter, the speed does not settle with the rated, and it is very low, less than 800. For this speed, if you apply a light load 0.5 Newton meter, then immediately my motor will come to rest. But when it comes to the superlift converter failure, induction motor drive, in the drive arrangement, if you are using this sort of converter, it perfectly settles with the rated speed, and the rise time is very, very minimum. There is no problem in it. And this is the torque results. And closed loop. I think the topic major, I have concentrated open loop only. If I start explaining closed loop, it may take much more time. Directly we will come into the point. Because I just plan to show you a few simulations, whatever we have discussed. Simple problem, a simple workout. Here, how you need to take a converter, DC-DC converter, what are all the problem you need to develop, how you need to choose the values of this inductor based on your output voltage. So here, we ourselves take a boost converter and we ourselves will set a problem. So I am setting my input voltage is 20 volt. Then inductor values 10 millihenry, capacitor is 20 microfarad, and the load, resistive load with 10 ohms, right? So whenever you are using an inductor in series with the supply, it should accompany with the small resistance, that is 0.4 ohm. Without that resistance, it will not allow you to simulate. And the conduction duty K is fixed as 0.6. Now my objective is, what will be the voltage transfer gain? This is how you can write mathematical modeling in your paper. Whatever converter you choose, you just start with assigning these values and set a goal, set an objective, what parameter you are going to determine. I am setting the voltage transfer gain as my first parameter, and what will be my output voltage, what will be my output current, what will be the converter efficiency. This is the problem designed by myself, and simple Kirchhoff's voltage law, current law derivation will give you the clear solution, right? So if you take in steady state in the sense, you need to first derive it, what will be my output current. This I2 is the output current, that is the load current. First we are going to derive the load current in steady state. That is obviously steady state in the sense when the switch is turned on. So in the circuit, we know when the switch is turned on, the circuit is isolated. So obviously the current that is generated, that is discharged from this capacitor will be my load current. So that is what given here. IC on will be is equal to the load current. Then the current of the capacitor during when it is turned off. So when it is turned off, the current in the capacitor is a part of current from the supply. So I want to consider the conduction duty. I want to consider the voltage transfer gain of this boost converter. So it is obviously equal to the K. That is here in previous slide we have seen it as gamma. K by 1 minus K into I2. So we know the value of K value, everything, right? Now, the input end, okay, during that, we know initially when the switch is turned on, the circuit is isolated, we least bother about the front end current, the inductor current. Now, the switch is turned off, the inductor input current, that is I1 and IL will come into both. So what is I1? So this becomes series with the source. Both are same. IL is equal to I1, which is equal to IL off, and we have to derive with respect to this IC off and I2. So this current is equal to a part of current goes over here, let it be I2 dash, and this is I2 double dash. So this I1 is equal to I2 dash plus I2 double dash. So that is what given over here. IC off plus I2 is that. IC off is I2 dash, this is I2 double dash. Already we know IC off value. So that is what given over here, right? So this one is substituted here, and both the terms are averaged, and finally they determine it is 1 by 1 minus K into I2. So that is my input current. Now the power relation, we need to show the efficiency, we need to determine the efficiency, that's why we need to go for power. So here the load what we are using is resistor, so simply it's a DC circuit. So P1 is equal to V1 I1, which is equal to P2 plus losses. So this is the condition we have derived, right? So input power is equal to output power plus losses is the general term, and based on that we know P2 is equal to the load voltage into the load current plus I square R loss will be my losses. So we are just deriving it. So V1 I1 is equal to V2 I2 plus I square R. So this IL square, input current IL is I1, and previously it was derived as 1 by 1 minus K into I2. That is what going to be substituted over here in this place. In terms of IL, it is substituted. And finally consolidating this expression, will be getting the power. It is equal to V2 I2 into 1 plus 1 by 1 minus K the whole square into RL by R, right? And the efficiency or total voltage transfer gain. This M is nothing but voltage transfer gain. It is output voltage by input voltage. So the left hand side we have V1 and right hand side we have V2. So V2, we're bringing it over here and taking this particular term to the LHS. We'll be getting V2 by V1 is equal to I1 divided by this whole term, this term. And solving all these things, the final expression will be 1 by 1 minus K plus RL by 1 minus K into R. And now we know the value of RL, we know the value of K, we know the value of R, we know the value of V1. Simply we can calculate V2 previously, and V0 also we can easily calculate. If you know the transfer gain, so this is, we know for boost converter it is 2. Obviously it is proven in this step. In this step it is clearly proven that the boost converter has the voltage transfer gain 2, and if you substitute the 2 over here for 20 volt, it will produce output voltage 40 twice. Efficiency is 2. Okay, and we know it is a DC circuit. I2 is nothing but the output current. We know V2 is equal to I2 into R. Substituting the values, will be getting 4 amps as my output current. So according to the objective, voltage transfer gain is 2. Output voltage is for 20 volt, it produces 40. Output current is 4 amps. And converter efficiency, what is my converter efficiency? Output voltage by input voltage. So output voltage is, that is 40, input voltage is 20. So it will be 200%. This is how you need to take a problem. Any particular converter, you have to give the values by your own, and then only you need to move on to the simulation part. Now I will show you the simulation, then we will come back to the PPT. my screen visible to everyone? I have changed the PPT.
Yes, sir. Yes, sir.
First, I'll show you the simulation that was designed for boost converter. Here, I don't want to give any fundamental points because almost all the participants are well familiar with MATLAB simulation. So here, whatever the diagram I've shown, accordingly, I've designed the simulating model. So the input DC 150 volt, and the same was given to the subsystem. This is the DC-DC converter part. First converter what I have chosen is a simple boost converter. A simple boost converter with inductor, switch, capacitor, a diode, and the pulse generator. You can see my switch is operating in 10 kilohertz and 0.5 is the duty cycle what I have fixed. It is 0.5, 50% pulse width. Now, instead of using inverter, I don't want to talk about this second stage because the topic what I am going to concentrate is only DC-DC converter part. So I least bother about this inverter, a simple universal bridge with 3 ohm, 3 leg, and a filter with basic values, and my motor is 0.5 HP 3-phase induction motor. For this, I have simulated already, and you can see the voltage. This scope will show you the input voltage, input DC 150, and what is the output from my boost converter. In PPT, I have shown you the eliminated ripple content. But when it comes to the original case, you can see for my 150 volt, this pink line, hope you can see this pink line. Pink line is the input DC voltage. For this input DC voltage of 150, my output DC voltage from the boost converter is high ripple. You can see it swings between 500, that is 450 and 150, right? So it is not settling with exactly twice, but it has to settle with 300, but it swings beyond 300, that is 150 volt, and below 300, 150 volt. So 300 volts it is swinging. So it indicates the average output voltage is 150, the input is 150, but my voltage oscillation in and around is 300 volts. That shows that the ripple is 200%. 200% ripple content is there in boost converter. It is not at all settling. And you can see directly you can see the speed response. For this oscillations, you can see the motor speed does not saturate. It is still rising. It does not attain the rated speed also even after 1 second. You can see the speed response of induction motor. The same circuit without varying any set of parameter, I have replaced only the subsystem and I have used the voltage lift converter, elementary positive output Leo converter in this place. In this place, I have used elementary positive output Leo converter with the same values of inductor and capacitor. But here we are using 2 capacitors, 2 inductors, a diode, and a switch. For this, you can see, as I said, the ripple is eliminated. Okay, for my 150 volt, this pink line, ripple is eliminated little bit, and it is settling. There is no voltage boost. It does not step up the voltage. It does not step down the voltage. The only job it performs is it maintains the voltage oscillation free. Okay. The question may arise, sir, here already it is 150 volt without ripple. Why you are using this converter? If this voltage is from any other source, if it is from rectifier, if it is from any other solar panel, we need to go with this. That is why we are using. So some sort of applications require this elementary positive output Leo converter also, right? Then the third circuit is superlift converter. In this circuit, in the subsystem for the same simulating model, in the subsystem, I have designed a superlift Leo converter. Very simple working principle. So here in this terminal 1 and 2, my input DC is connected and the switch is used when the switch is turned on,
machines.
the current that passes through the inductor. When the switch is turned on, current passes through the inductor.
Could be provided
And-
in stator and the rotor as well. And you can see
Yes.
if you don't have any permanent magnet in the rotor, then how the machine runs? You know the concept of induction, how the induction machine works.
Some interference is there.
Because of the flux lines from the stator will induce some flux in the rotor, and that flux will oppose or aid
Someone else speaking, I
flux
think.
lines coming from the stator. So, you know, generally you don't have any problem.
think, Anguraj-
Electric field and magnetic field is induced because of the stator. So I'll come back to the working slide, working of.
The current that passes through the inductor gets
You can see this diagram.
energize this inductor, and this diode will forward bias, and the capacitor acts parallelly. These two branches act parallelly, and during the turn on period both gets charged, and this diode, the second diode, will get reverse bias. During that time the output capacitor supplies the load current,
What
supplies the
happens?
load.
Only the A
And when this is turned off, you can see this inductor and this capacitor become series, and this diode reverse biases and this diode forward biases. And the stored energy from both the elements, both the parasitic elements, will brings the current, and that current passes here, that is I1. A part of I1 passes through the capacitor, and the remaining, the rest of the current passes through the load, right? It is obviously the same derivation we can use for superlift converter for mathematical modeling also. This is the working principle of superlift converter. And you can see the voltage.
will be energized and
You can see for 150 volts, the stepped up voltage is 450, around 3 times that of the input voltage. 3 times it steps up, and the ripple is less than 1%, you can see. Less than 1% ripple content was there using this superlift converter.
And once it is aligned, if you open the switch S1 and if you close the switch S2, what happens?
So this is what the simulation, what I came to show you. You can design, you can pick any one DC-DC converter from advanced DC-DC converter configurations, and you can put it here for your driver element. Nothing special. I have not designed any special drives. I have taken this motor from Simulink library browser. The filters, LC filter I have designed. Here also there is no calculations involved. It's a simple trial and error method. I have designed this filter and universal bridge. There is no specific inverter I have designed. And my inverter operates in open loop with respect to discrete PWM generator. So instead of designing a complicated network, I am going to show you only open loop. That is why, because due to the time restrictions, because the session is only 2 hours, already 1.5 hours I've taken. That is why I can't able to explain the closed loop control. I can't able to show you in the closed loop, show you the simulation of closed loop. If time persists, if I get a chance in phase 2, I'll explain that closed loop controls during the phase 2. Now let us move on to the PPT. Now the last part, I'd like to share some few things with the participants that it's my own experience how learn from this DC-DC converters. I started working in DC-DC converter. First attempt, I have prepared a paper. You can see the title of my paper: Simulation and Hardware Implementation of 3-Phase Induction Motor Drives Incorporating Superlift Video Converter. And this paper was communicated to Journal of Power Electronics during January 2015. During January 2015, I have not January, before January I have submitted, and very shortly I received the rejection from the editor. They have rejected this paper, and one key comment they have given. So what they have given, this paper presents Superlift Leo converter, which is researched by Professor Fang Lin Leo. On induction motor side, no novel concept of control schemes, right? So what I have did is, directly I have taken the Leo converter. Now I have shown you the simulation. The same way I have designed. I have just connected the Leo converter with the drive. Nothing, no closed loop control, nothing I have did. And based on the results, I prepared a paper and I submitted to Journal of Power Electronics, and immediately within a month I got rejection. The paper got rejected. And you see, this was happened January 2015. My first revision. Immediately I started working on that command, and you can see the title. My previous title was Simulation and Hardware Implementation of Previous Induction Motor Drive Incorporating Superlift Leo Converter. What converter with ripple-free DC link, right? So I included a closed loop control for Superlift Leo converter, and I have taken Leo because I give the credit to author Fang Lin Leo in my paper and not in my title. First job what I did is this one. The same work only, nothing different. Only thing, I used a PA controller for DC-DC converter, and from induction motor side, there is no novelty. Same induction motor I have used. And this paper was submitted during the month of March 2015, end of March 2015. Within 2 months, that is 20th May 2015, I got major revision comment, right? So in that comment, what they have said, the same point, it seems to me the author just combined the DC-DC converter and DC to AC converter without novel controller for both of DC and DC to AC. So very clearly they have given the same comment, but previously they rejected my article. But this time they have given major revision. I need to revise it, right? Again, what I did, I have implemented a small closed loop control, that is B by F control in induction motor drive, and I resubmitted. Just see the month. This was May, and June end, I have resubmitted my paper by the month August. August month, my paper was accepted. My paper was accepted. So nothing special in it. So why I am coming to say this particular point to the participants is, I have shown you few converters, DC-DC converters for drive arrangement. Simply taking one converter which is already existing and connecting, cascading that converter to the drive will not give you a research, will not give you any credit to you when it comes to publication point of view. So when you are going to cascade a converter, DC-DC converter for any sort of application, just include a small closed loop control, include a small controller, even if it is already existing, just show that it may do some job in that converter. So I suggest the people to choose any one configuration from advanced DC-DC converter part, and they can use any simple like controller like PA controller. Nowadays, most of them are using fuzzy logic controller, sliding mode observer. So many, n number of controllers are there. You can use any one and just give some optimized algorithm for that and make it as a paper, get some results with comparative analysis. Your paper may hit the doors of very good reputed journals like even sometimes IEEE. So that is why, that is the thing what I am coming to say in this 2 slides. Now, the last few tips for publications. You can see what are the tips when it comes to simulation. So if you are a person who is working in power system, most of your results are from software oriented, simulation results only. If it is through MATLAB, then presenting your results plays a vital role in publication part. So here I am showing you a simple system designed with 2 or 3 blocks with integrator. I have taken the results in the scope part, and after simulation, people used to do what is the thing? What I did is same way most of the researcher PG students, they used to bring the result in scope, and they may crop it and they may put the same result in paper. Sometimes people may do Photoshop also. They may invert the color of the background. They may put it as a white. Sometimes this may be done. If you are doing so, your paper will not be considered for any further publications, because this result does not show any title, no x-axis, no y-axis. This is what the job done by most of the students from PG, UG, some beginners they used to do. They will crop the picture using print screen, and they will paste it in Paint, and they will edit. They will further crop it, and they will again paste it from Paint to paper. If you are doing so, 200%, I will say your paper will not be screened. It will not cross the screening level. You see, this will be the modification. Even if you are doing any Photoshop work, only difference, you are giving the color variation. This result does not show any work. This no idea of the picture. This is one particular result presented during final Viva of a class topper. We all know it's a trapezoidal waveform, but this result does not show any idea behind it. What it actually indicates, what is the scale of it, nothing. But this was presented by a class topper. What we need to do actually, this is the job, what we need to do with simulation. I can show you simple tidbits. Just go to setting. In scope window, before running your simulation, go to settings, just click on this data history. In settings, you can find general and data history. Just click onto it. Then you can find under data history, usually this limit data points to last 5,000 will be enabled. Just disable this and enable the save data to workspace and give your variable name for that scope. That scope alone, you give your own variable name. It may be any alphabet, it may be any name, but that should not include any special characters or space. And under that format, you need to select array. After this step, just press apply and then OK. Next, you have to run the simulation. So after doing so, whenever you are working with the simulation, open the scope, and the scope must be modified accordingly what I have presented in the previous slide. Then after running the simulation, just type this command. This one line command is enough. I have listed some 7 lines, but the first line is enough to extract my result. So just plot the variable name what you have given. In that previous slide, I have given B, capital B. So bracket, colon, comma 1, close the bracket, comma, B, colon, comma 2, comma, B, colon, comma 1, comma, B, colon, comma 3. So this shows that this 1 indicates the x-axis. Okay, it's an array, right? So whatever data it is processed through scope, that will take it as a matrix array. So in X scale, it is time, and it takes that time data as a single column. Okay, it's a single vector, first vector. And I have 2 different results in my Y data. Means first result it is taking it as in second column, and my second result in third column. For example, in a particular scope, I am just combining the torque variation with respect to load. Torque variation with respect to load of 2 Newton meter. Torque variation with respect to load of 5 Newton meter. So 2 results I just combined, multiplexed and presented in my scope. Then you can use this particular formula. And if my plot has 3 results embedded together, then 2 more items I need to include. B colon comma 1 comma B colon comma 4. If you are typing this particular command in your command window and press enter, your result will be very clear like this. You can see this result that is extracted, and you can do all sort of magics, all sort of jigna work in this image. You can add title, you can even want to eliminate the transient period, means only you can keep the steady state period, because to attract the reviewer, you can sometimes it is required to show only the steady state performance of any block, any particular parameter. So for that cases under, you can modify the picture accordingly, right? So this is how you can present your simulation in your paper. So by this I am completing the session. The next 10 to 15 minutes, you can ask any questions.